Today we are going to present a different version of the Poisson model in order to modeling better number of claims or events in a given time interval. The reason to do this is because the Poisson model works well if certain conditions are satisfied, which in reality are not so easy to satisfy. For example, the requirement for a Poisson distribution in order to be valid is that the number of claims of events occurring in any two disjoint time intervals are independent. But let's suppose that we are in California in a forest and we want to consider the number of fires during the month of July and August. Okay, so the two disjoint time intervals are July and August. We want to want to model the number of fires in each month. There is a common factors that affect both July and August, which is the drought caused by summer, and therefore we cannot say that the number of claims, the number of fires occurring in these 2 months are independent. Therefore, there is this common factor related to the weather. Another one could be, for example, we are in a tropical country where in the months where there are big rains, and the number of claims of accidents during these months will be correlated by the can be correlated by the heavy rain. Another example of variable which can makes number of claims correlated can be economic one, for example during the months of COVID. Therefore, how do we do in order to model this variability and this interdependence? We introduce a structure variable q tilde, which it is defined on the positive side of the real line, and its mean it is equal to 1. Therefore, we do not want to we do not want this structure variable as an impact on the mean of the number of claims. Therefore, our k tilde will be equally distributed, therefore with a Poisson distribution with parameter n multiplied by the random variable q, mixed Poisson, and a good choice for the structure variable q tilde will be gamma, with a shape parameter equal to the rate parameter, and its mean it will be equal to 1, because the mean for a gamma distribution, for a gamma random variable, it is the ratio between the shape and the rate parameter. Therefore, now we want to prove that the distribution, the probability density function of therefore this mixed Poisson with gamma as structure variable is distributed as a negative binomial. Therefore, in order to do that, we take the conditional mean, we condition it to the structure variable q tilde. Therefore, here we take the integral from 0 to plus infinity, which is the domain of the random variable q, and we take the integral. Therefore, in this passage there have been some steps. Therefore, we have taken out all the as can be seen here, all the factors which do not depend on the q, and then we have aggregated the exponential and the q. In order to understand better this point, we have to remind that the probability density function of a random variable q tilde distributed with gamma with equal parameter with parameter shape and rate parameter equal to h, this distributed in this way with the Euler function, therefore it does not depend on q and we take it out. This term h to the power h we take it out, and then the other things are straightforward. Then we make a change of variable, therefore we transform q as z, the new random variable, divided by n, which is the initial parameter of the Poisson, and h, which is the shape and the rate parameter of the structure variable q. And therefore, at this point, we can see that by taking another step, that we have something close to what is a gamma, a gamma PDF inside this integral, because z n plus h, it is our new variable of interest, and therefore we have made this trick in order to understand what is the rate parameter, therefore the beta parameter for the gamma function, which is in this case 1 over n plus h. And then we can see that here there is it is beta, it is n plus h, while h plus k, it is the alpha parameter, therefore the shape parameter, and therefore at this point we can exploit the properties of the CDF, because here in this term inside the integral, some factors are missing. For example, the rate parameter power the shape parameter, and then the Euler function. Therefore, by exploiting the CDF property, which is that the area under the curve, so the integral from 0 plus infinity of a given, in this case our continuous random variable, it is the gamma for the structure variable, so the area under the curve, it is equal to 1 by the definition of by the properties of the probabilities. Therefore, taking in mind this fact, we have that the integral of this part, the integral of this stuff, is equal to 1 times the Euler function at the numerator, because in this left hand side it is not present at the denominator, while at the denominator there will be the rate parameter multiplied by the shape parameter, therefore n plus h power h plus k. And therefore, referring to the original equation, which is this one, so we have understood what is the value of this integral. Therefore, this remains the same. In fact, it remains the same. Here it is the value of the integral from 0 to plus infinity, and therefore here we have this result. Then by simple algebra we arrive to the final step, which proves that we have a negative binomial distribution for what concern the mixed Poisson random variable. where p it is h over h plus 1. And this is all. Thank you for your attention. If there are some comments or other things that you want to understand, please comment it in the tab below. Thank you.